Hello everyone, welcome back. So today we want to talk about the second derivative test, another way to find local maximum minimum values. So first thing we want to do, our goal is understand the relationship between the second derivative and to concavity. We'll introduce what that means. And then we'll also use the second derivative test to find local maximum and minimum values. So first, let's talk about concavity. And this is something you may not know the word, but you're familiar with the idea. We talk about functions where they open up or open down, especially probably talk about that in algebra with quadratic functions. Then that's what we're talking about here. So concavity tells you whether a function it says opens up or down, opens upward or downward. And this actually, you find this from the second derivative. So if a function is concave up or opens up, if the second derivative is positive or second derivative is positive there, okay? And then it's called concave down if it opens down, and the second derivative is negative. So let's take a look at some examples of that over here. And probably the best way to talk about that, the easiest way is to talk about functions we're familiar with. Look at y equals x squared. Okay. Obviously, this one opens up. So you probably learned this when you were learning about quadratic functions. It opens up. Okay. What that also tells us, it also means it's concave up. Okay. And then if we take the derivative, first derivative, of course, is just 2x. The second derivative, which is the derivative of the first derivative, is just 2. In this case, that's positive. Okay. And so, once again, the second derivative is positive. Okay. So if our second derivative is positive, it means the function is concave up, opens up like this. Now, let's look at a similar one for the next example. We'll just look at y equals negative x squared. So a parabola is just the same as y equals x squared, except with a negative. So let's look at y equals this, negative x squared. And once again, hopefully remember from algebra, if you put a negative in front of a function, it gives you a reflection through the x-axis. Okay, this one obviously opens down. Okay, that means it's also concave down. And to take the derivative, y prime is equal to negative 2x. And of course, then y double prime, the derivative of the first derivative, is just negative 2, which of course is negative everywhere. So once again, as it shows us, then if your second derivative is positive, the function opens up. The second derivative is negative, it opens down. Now, you can also have places where the concavity can change, and that's something called an inflection point. Okay, so a function changes, especially if it's a continuous function, if it changes concavity at some place C, that's called an inflection point. Let's talk about that. So let's look at a function again, a basic function. Say a function looks like this. Actually, let me just get rid of the, don't want to need the axes that much. Okay, let's say this is our function. This is our f of x. Okay, now obviously right here, at this point, it's obviously concave down right here. That means the second derivative is negative. And then here, it's obviously concave up. That means the second derivative is positive. Okay, so right here is where it changes. Okay, it changes concavity. And let's call this point C. So what we say then C is let's call it inflection point. So C is an inflection point. That's where the function changes concavity. It can change, in this case, it changes from concave down and concave up. It can also go the other way, from concave up to concave down. The basis where the function changes concavity. Now, you can also have changes in concavity in other ways. So we could also have a function. Let's look at another function. It is also possible to have a function that changes concavity where maybe it's not continuous. Okay, something like this. Okay, so that would be a concavity change. Okay. Or I'll click maybe let me do that again because I want to continue this function onward. Okay. And you can also have something like this where it could change concavity as well. Okay. So here you'd also have a concavity change. So change concavity can also change or not where the function is not continuous or we have an asymptote. Okay. A good example of that, a cavity change like that, is actually, let's go to Desmos, a function 1 over x. Okay. So here, of course, it's not, if x is 0, it's undefined. A vertical asymptote at x equals 0. And obviously the concavity change is different here. Here it opens downward, and here it opens upwards. You have a cavity change there, but it's actually not continuous. We're mostly focused on continuous graphs here. All right, let me say a couple more things about, now also, it says note, if the second derivative is 0, then that doesn't imply a continuous function like here. Now, also a nice thing about this, that actually, let me go back here, f double prime of c in this case is equal to 0. So much like when the first derivative changes from positive, negative, vice versa, if it's continuous, it goes through 0 usually. And the same thing can happen here, though it's not guaranteed. Okay, just because the derivative is 0 is not guaranteed. Okay, let's look at an example like that. So if we have y equals x to the fourth, okay, if you graph this, let's graph that. And if you've seen this graph before, it's similar to a parabola. It's kind of a, oops, it should be an equal sign. It's kind of a flattened parabola. Okay, so it has kind of the parabola shape, but it's flattened. But if you notice, then it's concave up the whole time. Okay, so if we take the derivative, so the graph looks like this. It's kind of a flattened, once again, it's kind of a flattened parabola. But if we take the first derivative, of course, 4x cubed, and then the second derivative is going to be 4 times 3x squared, which is 12x squared. You notice this is greater than or equal to 0, can be 0 always. It's never negative, okay? Then at x equals 0, y double prime is equal to 0, but is, as you can see from the graph, and also from the fact that it's always positive, is concave up or opens up everywhere. Okay, so just remember that just because the second derivative is 0, that doesn't imply a concavity change, although basically have a nice continuous smooth function. If the concavity does change, it has to change where the second derivative is 0. Okay, now one more thing I mentioned. This is also not this concavity isn't necessarily related to whether the function is increasing or decreasing. Okay, so let me draw one more thing real quickly. So let's draw a couple graphs. Let's say 2 graphs here. Let's say we have a function looks like this. Okay, so this function is increasing and it's concave up. So increasing means the first derivative is greater than 0. It's concave up would actually mean the second derivative is actually, I'm sorry, it's concave down. Not up. I'm sorry, concave down. It's opening down. Okay. But you can also have a function that's increasing like this. Both these functions are increasing. But this one is obviously concave up. Okay. So that's an example where, so just keep that in mind that increasing, decreasing in cavity are not necessarily related to you. They don't be a function be increasing and be concave up or down. And the same thing if function is decreasing as well. I won't draw that picture, but the same idea. So basically, if a function is decreasing, could be decreasing with a concavity is up or down, either way. But just keep that in mind as well. Those are two different ideas. Okay, so let's talk about this idea. So what does this tell us? Well, let's look at make up one more graph. What does this tell us about a graph? All right, so let's say a function looks like this. And of course, it can be different ideas. Let's say it looks like this. Okay, so obviously right here, it's concave up in this section. And it's obviously concave down in this section. And right here, let's say right about here, we call this C, you have an inflection point where the concavity changes. All right. Now, if you notice here where it's concave up, you notice right here, of course, if it's concave up, then your second derivative is positive. If you notice right here, then you have a place, as you can see, where the first derivative is 0. Okay, you have a horizontal tangent line. And also here, what's concave down, your second derivative is negative. But like over here, we also have a place right here where the second derivative is equal to 0. So what we can see then is anytime the function that's concave up, if it once again, if it's nice and continuous, smooth and all that, if you have a place where it's concave up, both concave up, and where the function is first derivative is equal to 0, that implies that's going to be a local minimum. Okay, and here you have a place where the function is concave down, and a place where the first derivative is 0. That's going to be a local maximum. Okay. And so that's what we're going to use in what's called the second derivative test. That's going to help us there. Basically, another way of identifying local maximum minimum values, if you know the concavity on a certain part or certain domain, certain part of the graph, then also if in that same area, if there's a place where the derivative is first derivative is positive or negative, then we can tell whether or not it's a local maximum or a local minimum. All right. Let's take a look at that over here, the second derivative test. So suppose f is continuous in open interval. An open interval means not including the endpoint. We're containing some number c, and at c, the first derivative is 0. And what we can say then is, it's just as we said here, if the second derivative, if you're in a place where it's equal to, first derivative is equal to 0. And actually, let me, not to be confusing, let me change this, call this c. That might be confusing. So we have our inflection point right here. So don't confuse it with the C I'm using here. Inflection point there where it changes. Okay, so if the first, so once again, we have a place where the first derivative is equal to 0. If the second derivative is positive, base is concave up, and that means it's local minimum as we see right here. But over here, if it's concave down, which means the second derivative is less than 0, then it's the local maximum, as we see right here. Now also it says if the second derivative is 0, the test is inconclusive. Okay, and actually that's what's true right here at our inflection point. And at the inflection point, the second derivative of this function, where the concavity change is equal to 0, okay, and that's inconclusive. That place could be an inflection point, it could be a local maximum, local minimum, or neither, okay? So wherever the second derivative is 0, then the test is inconclusive. We don't necessarily know from the second derivative test what that is. Okay, it could be any of those. It could be a local maximum, local minimum, or neither. As we saw mentioned, y equals x to the fourth, the second derivative is equal to 0 here, and that was actually a local minimum, so we can't tell that from the second derivative test. So if you have a case where the second derivative is 0, if they're, well, specifically, back up, at that same point, for the place where the first derivative was 0, if the second derivative is also 0 there, then the test is inconclusive. All right, so that goes back to, once again, to y equals x to the fourth. All right, so here, obviously, at f prime of 0 is 0, but f double prime of 0 is also 0. Okay, so at that point, the concavity uh, is 0. So the second derivative is 0. There's no concavity there. We can't tell what it is. Okay, as we saw right here, you plug in 0 for your first and second derivatives, you get 0. And so the second derivative test itself doesn't tell us what that is. Okay. In this case, the test I'm having trouble writing today. The second derivative test is inconclusive. Okay, this is basically about the second derivative test. All right, so now let's take a look at some examples using the second derivative test. Okay, now the first one, and if you've seen my previous video on the first derivative test, I'm actually use the same examples here and just expand on that idea. So first off, my f prime of x is equal to negative x cubed over 3 plus x squared over 2 plus 2x. Okay. Sorry, that's f of x. Okay. Now, so the second derivative test, of course, you need to find both the derivatives, first and second. So that's the first thing we want to do. All right, so f prime of x is going to be, and I was going to go through this a bit faster. So derivative of x cubed is going to be 3x squared. The 3's will cancel out. It's going to be negative x squared plus 2x plus 2. Okay, that's our first derivative. Okay, then our second derivative is, or take the derivative of this, can be negative 2x plus 2. Okay, now, so we found both of those. Now we also need our critical points, because remember, critical points a place where the first derivative is equal to 0. So now actually let's go ahead and graph this function first, and we'll take a look at it. So let's actually get rid of this. So let's graph y equals negative x cubed divided by 3 plus x squared divided by 2. Oops. Yeah, so always make sure you use arrows to get out of the exponent when you do that. Squared divided by 2, then plus 2x. Okay. Now, once again, if you've already seen my previous video on the first derivative test, we found the critical values there. All right, so basically our critical values, and we'll go through the whole process here, but our critical points are going to be at -1 and 2. Okay, critical points, remember what you do is set this equal to 0 and solve that. Critical points are going to be x equals -1 and just x equals 2. Okay, now what we also want to know is where the function changes concavity. And where the function changes concavity is going to be where f prime of x is equal to 0. So let's solve that. To solve f double prime of x, we'll solve negative 2x plus 2 is equal to 0. And that's easy to solve. And so just you have negative 2x is equal to negative 2, x equals 1. Okay. So this is our inflection point. And let's take a look at that. So make sure that matches what we see on our graph. Our inflection point should be about at 1. And yeah, it looks right here. Like that's about where it changes. Um, Hang on. Let's see. Okay, let's roll with it. All right, so that should be our reflection point. There, actually, I need to pause this just a second. I'll be right back. Okay, welcome back. You may have noticed a little glitch there. I had to pause it for a second. Yeah, I apologize. I realized I've been off today. I realized I made a little mistake. So this should actually just be just x, not 2x. Okay, that didn't look right. If that's something I always want to make sure. I'll explain why I thought something was wrong. Let's go back to our graph. Looks like the cavity changes right about here, but that showed changing right here at 1, and that didn't really look right. So that's always a good thing to do, is make sure your graph matches up what you see. And so, yeah, so we do that. This should be negative 2x plus 1 for my second derivative. And that makes more sense with the graph. So let's change that. Plus 1 minus 1 makes it x equals positive 1/2. That's my inflection point. Once again, that does match up with the graph. All right, so our inflection point looks like it should be about right here at 1/2. Let's zoom in a bit. Yeah, right here at 1/2. Right in between those two. Okay, good. All right, that's our inflection point. Now, what we do is we can do some, if you've done a sign test or sign chart for the first derivative test, we do something kind of similar here, all right, to help us out with this. So a sign chart. All right, so first off, let's separate here. So here at x equals 1/2 is where concavity changes. Okay. So we need to find the sign of f double prime of x. Which is, of course, equal to 2x, negative 2x plus 1. Okay. Now, that's where concavity changes. Now, also what we can do is we put in right here, once again, this is where our second derivative is equal to 0. Okay, let's put in our critical values as well. All right, so here, right here at x, this is going to be at negative 1. Remember, that's where negative 1 is where one of our critical values. And over here at 2, that's also a critical value. Okay. And so we can also use those as test values to figure out what our concavity is. Okay. So you plug in, for example, right here, if we plug in negative 1 or negative 2, we may need to write that out. All right. So that's going to be f double prime of negative 1. Give me negative 2 times negative 1 plus 1. And so that's going to be negative 2 times negative 1 would be positive 2 plus 3 is going to be 3. More importantly, that's going to be positive. That's going to be positive. Second derivative will be positive. Then over here, let's plug in our critical value over here, f double prime of 2 into our function. So that's going to be negative 2 times 2 plus 1. Negative 2 and 2 is negative 4. Plus 1 is negative 3. And of course, that's negative. So here our concavity is going to be negative. Well, second derivative is going to be negative. What does it mean about our concavity? So positive derivative, that's concave up. The function opens up. Negative, it's concave down. The function opens down. Okay. So now what does that tell us for our second derivative test? Well, at negative 1, write this out, at x equals -1, at that point, f of -1, f prime of -1 is 0. It's a critical value. And f double prime of -1 is positive. Okay, so what that implies, let's look at our second derivative test. So the first derivative is 0 at -1, it's a critical value. If the second derivative is positive there, then once again, that means you have a local minimum there. Local minimum at x equals 1. Okay, look at our other critical value at x equals 2. Okay, so once again, what we see is that f prime of 2 is also 0. It's a critical value. And f double prime of 2 is, we said, was negative. Okay, so from our second derivative test, critical value, if the second derivative is negative there, that means we have a local maximum there. Okay, and once again, let's double check, make sure with our graph, make sure it looks right. Yeah, that's the case. Let's zoom out a bit again. So we hit a reflection point right in the middle at 1/2. Right here, a local minimum, -1, local maximum at 2. Right, that checks out. Okay. Let's look at our next example, number 2. And this one is going to be f of x is equal to -2 times the cosine of x minus x minus x. Okay. So once again, let's find both derivatives. All right, so f prime of x is going to be negative. Remember that I'm just a bit quicker, but you have a -2 out front. The derivative of cosine x is negative sine of x. And so that's going to be positive 2 times the sine of x minus 1. The derivative of negative x is -1. Okay. Then the second derivative, take the derivative of the first derivative, and the derivative of sine of x is cosine x. That's just going to be 2 times the cosine of x. And of course, the derivative of -1 is 0, so that's just 2 times the cosine of x. Okay. Now, the critical values. Okay, so that's where you have 2 times the sine of x minus 1 is equal to 0. And those solutions, also I forgot to mention that here we're just looking at the interval from 0 to 2 pi. I forgot to mention that. Let's plug that in. Okay, but here in 0 to 2 pi, and once again, you can see my previous video over the details of this, but basically you solve this in 0 to 2 pi, your solutions are pi over 6 and 5 pi over 6. Those are your critical values. Okay, now we also need to find the inflection point or points. And to do that, then, we set the second derivative equal to 0, once again, on that interval. Okay, and so that's going to be 2 times the cosine of x is equal to 0. Divide both sides by 2, that's not going to change anything. So the cosine of x is equal to 0. Okay, remember on the interval from 0 to 2 pi, where is cosine 0? And that's going to be basically at pi over 2 and at 3 pi over 2. That turns out we actually have a couple inflection points. Okay, now here we actually have 2 potential inflection points. Okay, now also let's go back and look at the graph. Let's look at the graph of this first. So let's get rid of this one. Okay, so this is y equals -2 times cosine of x minus x. And also remember that Desmos defaults to degrees. So if you want to change from degrees to radians, use a little wrench, but you're in radian mode, it defaults to that. So leave it in radian mode. Okay, and also another thing you can do is figure out where our function we're interested in from 0 to 2 pi, just draw horizontal lines. You can do that by putting We know our interval goes from 0 to 2 pi, so I draw a horizontal line at x equals 0, which is, of course, the y-axis, and x equals 2 pi. I do pi, just do 2, and then letter pi. Okay? Right, so what it shows, what we expect to have, is a local minimum here, local maximum here, an inflection point in the middle, also an inflection point right here, which we're not as interested for because there's not a, because we're only looking at this interval right here. We don't care as much about this local minimum. We don't care at all about this local minimum here. It's outside of our domain of interest. All right, let's take a look. Let's go back. Here, let's do like once again, do a previous example, do a sine chart. Because we need to evaluate our function, our second derivative at our critical values. Okay, so we actually have two places, two critical values, or two inflection points. These are our inflection points. We should have two of those, pi over 2 and 3 pi over 2. And once again, these points, f double prime of x is 0. Okay. Remember, also only going from 0 to 2 pi. So that's all we care about. All right. Now we have two critical values. So one between 0 and pi over 2, and that was pi over 6. And of course, this is where the first derivative is equal to 0. And the other one is at 5 pi over 6. And that's also where the first derivative is equal to 0. We don't have any critical values in this interval. Don't really care what happens there. All right. But let's find out what happens in these. So once again, here, our second derivative, f double prime of x, is equal to 2 times the cosine of x, I believe. Let's double check that. All right, so 2 times the cosine of x. Okay. Now here also, we only care about the sine of f double prime. Okay. What we're going to do, once again, our second derivative test, we need to plug these values in and see what we get. So 2 times the cosine of pi over 6. And what we'll do is we'll just use Desmos for that as well, or your graphing calculator, or any calculator, scientific calculator. It's going to make sure in radian mode. Let's do that. We can actually do that on Desmos. So let's move down a bit. So 2 times the cosine, and then what's going to do pi over 6, just do pi for pi, divided by 6. And about 1.73 of the main thing, that's positive. Okay, about 1.73 of it is positive. Of course, is positive. Okay. Now, we know the concavity changes right here at an inflection point. So, or will potentially changes the inflection point. Okay. So let's see, and it will, as we'll see, it will. All right, so that's going to be 5 pi over 6. To do the same thing, plug in 2 times the cosine of 5 pi over 6. Let's find out what that value is. And it's probably going to be negative, but let's make sure. In fact, the only thing I'll just add a 5 right here. Yeah, in fact, negative 1.73, which is negative, what we expected. So negative 1.73, of course, is negative. Now over here, we're not really going to fool with this over here. We don't really care right now, although there's an inflection point, most likely. Okay, so the sine of f of x is positive here, negative here, right? So this definitely is, so here I should actually say these are possible inflection points. Let me see if I did that in the first one, because we have kind of need the sine chart to make sure they're inflection points. Okay, yeah, this is also a possible inflection point up here on the first example. Okay, now, so what that tells us, in cavity changes there. So we have an inflection point at pi over 2. Once you can check on your own, you'll also probably have one at 3 pi over 2. You can check that on your own. Just plug in some value between 3 pi over 2 and 2 pi. All right, now let's think about our local minimum or maximum values. Okay, so at x equals pi over 6, okay, the first derivative is 0 there. We know that's a critical value. The second derivative, f double prime at pi over 6, is positive. All right, so look back at our second derivative test. The places the critical values where the first derivative is 0. If your second derivative is positive, we have a local minimum there. So we have a local minimum at pi over 6. Okay, let's do the same thing for 5 pi over 6 and find out what it is. X equals 5 pi over 6. Okay. We know our first derivative, 5 pi over 6, is 0 because it's a critical value. And then the second derivative we found at 5 pi over 6 was negative. Okay, so go to our second derivative test. And if the second derivative is negative, there we have a local maximum. Okay. And we're going to see if that matches what we see on the graph, and it does. Okay, on this part right here, it's in between these two parallel lines, these two lines. Okay, right, we have a local minimum there at pi over 6, local maximum at 5 pi over 6, and inflection point, can't really see it, but should be at 5. Well, actually, we can also draw a vertical line at pi over 2. X equals pi over 2. And right, that's right there in the middle of those two. That's where the concavity changes, right there in the middle. Okay, so let's kind of review what we learned. Let's mention one more time. Again, we think about x to the 4th. Go back where I mentioned that one. Yeah, so if we done a second derivative test on x to the 4th, okay, we notice that the first derivative would be 0 to critical value right here at 0. But the second derivative would also be 0 there as well. And so what that would be, that'd actually be an inconclusive. The second derivative test wouldn't tell us that. We'd have to use, for example, like the first derivative test then to figure out what kind of local maximum, local minimum, or neither we have right there. Because it could be, if the second derivative test is inclusive, if the second derivative is 0 at that point, that critical value point, then the test is inconclusive. It could be a local maximum, local minimum, or none of those. So let's review what we've learned so far today. So learn about the idea of concavity. And so when a function is concave up, it's saying it opens up, and your first derivative is positive, second derivative is positive there. If the function opens down, it means it's also concave down. The second derivative is negative there. And a place where those two change, where the function is continuous and change, is called an inflection point, where the concavity changes. Then we learned about the second derivative test as a way of finding, or basically evaluating, whether a point is a local minimum or maximum. And then we found that you can use the concavity to determine whether critical value is a local minimum or maximum, unless second derivative is 0 at that point. When that second derivative test is inconclusive, you'd have to use another test or some other method to determine whether the point is a local maximum or local minimum. Thank you. Have a good day.